guys are keeping track of the good and bad ideas I've had for some of these lectures, I would go ahead and put this one up to a really good idea. What an absolutely beautiful day out here. So, welcome to Module 3. This is entitled Where the Ocean Meets the Land. So, I'm out here on the water. Somewhere up in Warren, Barrington, somewhere. I think I got a little lost, but that's okay. Because this first lecture, we're going to talk about the coastline. And I am calling the whole module Where the Ocean Meets the Land, but really that is specifically defined as the shore. So technically the shore, right where the water meets the earth, okay? But the coast is a little bit bigger than that. So the coast is actually the larger zone affected by the processes that occur at the shore. So I'll throw up this figure here. You can see this goes from the beaches to the lagoons all the way through the marshes, and we're going to talk a bit about some of these. And that is the coast. And the coast encompasses, like I said, the beaches. We have wetlands, cliffs depending on the type of coast. It can be rocky, can be sandy, can be grassy, can be frozen, all right? Get into the Arctic and Antarctic. That's a coast. That's a coastline. So we're continuing in this module. We're still we are still on the continental margins, and we're specifically going to start looking at communities at the shoreline. And these are going to be 3 communities, and I say we're going to be looking at them. I'm really pretty much just going to tell you about them here, and then we'll move on from that. But these are rocky intertidal zones, sand beaches, and salt marshes, okay? And Rhode Island has all of these. We have a lot of coastline here. So the rocky intertidal zone, all right, that is the area between the highest high tide and the lowest low tide. And if you guys spent any time on our rocky shores, you'll kind of see that. You'll see that there's a lot of things that live there, and sometimes they're covered with water and sometimes they're not, all right? And this is actually one of Earth's most densely populated areas, and it's pretty impressive because it's pretty violent, right? That wave shock that happens on these coastlines, these organisms really have to do a lot to survive that. It's pretty interesting. But even more so, all of these environments, again, the rocky intertidal zones, sand beaches, and salt marshes, unlike everything else we've talked about in oceanography, these aren't always covered with water, right? Sometimes they're submerged and sometimes they're not. In fact, I'm out here kayaking, and I've been out here before where there's little islands all around. And now all I can see is some grass popping up, and I've actually kayaked over it, and you can see the bottom, and you can see where these plants are now covered with water. And that includes the animals that live there as well. So the other one is sand beaches, right? And you guys have maybe seen some beaches around here in Rhode Island, either down along the Atlantic coast or right there in Narragansett Bay. And you know, it may not seem like there's a lot of life there. It just looks like sand, but there actually are. There's a lot of small creatures that live there. And it's actually a pretty harsh environment for them. If anybody's ever done any, I don't know, work in a machine shop of some sort, and you've used a sandblaster, that's kind of what it's like, right? They're just constantly being bombarded with these waves of sand. So it can be pretty harsh, but they've found a place to survive. And finally, the reason I'm out here is salt marshes. And salt marshes are incredibly important in Rhode Island, all right? And they encompass, you guys can look around here. Hopefully my little camera setup works and I can show you around. So you see all the grass around here. And like I said, sometimes they're little islands and sometimes they're submerged. But those are vascular plants, you know, sort of like the seagrasses. Well, they are, I guess, seagrasses, they're just not always underwater. But they are, as opposed to algae, they are vascular. They have the xylem and phloem. They flower, okay? And, you know, other places, not necessarily Rhode Island, but salt marshes can have mangroves, right? So you go a little further south, a little bit warmer weather, and mangroves are part of the salt marshes. The important thing is here, a salt marsh has a muddy bottom, all right? And they're big. You know, you think of a rocky shore or the sand beaches, and you can pretty much see all of it. Well, if you look all around here, this is all a salt marsh, at least outside of where it stays water all the time. And the tide's pretty big here, so there's a lot of area sometimes uncovered and sometimes not. And this is incredibly high in primary productivity. 4 times more than the most productive farmland It's pretty impressive. And that's because, we've already talked about this, the nutrient runoff, right? It comes right from land, all those nutrients. No upwelling needed. And, well, there's plenty of sunshine, right? So we already talked about how far water penetrates, how far the light penetrates into the ocean. And generally in salt marshes, it's much, much, much shallower than that. In fact, I'm kind of kayaking around here. Sorry, I got distracted. There's a bunch of fish freaking out over there. Anyhow, I can see the bottom for most of what I'm kayaking around here. It's pretty shallow. What else? So these salt marshes, they have a profile, and I can throw, whether I put the image up here or just put it in the lecture notes, you can sort of see that and how this works. There are areas that are sometimes inundated with water and sometimes not, and there's different levels. But we're not too concerned about that. I'm not going to make you draw that or anything, but that is for your information. You guys want to see, we do live here in Rhode Island. But the big thing is, this is something called an estuary, and this is that very productive part of the ocean. And an estuary is simply a body of water partially surrounded by land, okay? And maybe this looks familiar to you here. This is Rhode Island, and pretty much Rhode Island is an estuary. Narragansett Bay is a massive estuary. Now, I am quite a bit further north up here, out of the bay itself, but this is, I don't want to say this is where the magic happens, but in these little tributaries that feed into Narragansett Bay is where you get these salt marshes. You get this high productivity. This is a mixture of salt and fresh water. So the salt water obviously comes in from the ocean, and behind me is a river that I can't remember what river this is. I guess I'll have to look that up later. I'm sure I'll put it up there in the top. So it's not quite as salty. So it's not that 35 PSU, 35 per mil that the ocean is. It's something less than that. And there's going to be a bit of a gradient depending on how far you are, how close you are to the open ocean, or how far you get up here to the freshwater input rivers. The tides have a bit to do with that. In fact, I timed it right today, where as I paddled up the river, I'm turning around and headed back, and the tide's with me and the river's with me, and so it's a nice, easy day, and the winds are pretty low. It's absolutely beautiful. Oh, what else about this? So we talked about the salinity, but again, this is highly productive. And you guys remember those meroplankton that we talked about, those plankton that don't spend all of their time as plankton. So juvenile fish and crabs, the larvae, right? This is where they flourish. This is where they grow and get big and strong to be able to go out into the open ocean. And believe it or not, this is still really important for commercial fishing. We think of these commercial fishing as these open ocean sort of thing, and everybody talks about sustainability, which is incredibly important. But part of that sustainability and part of that, holistic taking care of everything, I can't think of the word, is because of these estuaries. So these, about 80% of those commercial fish, those big fish populations, somewhere along that trophic pyramid, along that food chain, depend on these coastal environments, depend on these salt marshes and estuaries to survive, because this is where the primary productivity starts. This is where that energy begins and makes its way through the trophic pyramid. What else? So the other thing about coasts is, this is where humans experience the ocean for the most part. For most of human history, there weren't at least ocean-going vessels, but there were definitely boats. And, coasts were a place for food and travel and exploration and shipping, right? This was the way. I mean, roads were not very good inland. So most of humans spent their time on the coast, and they still do. I'm going to put up a map here of the coastal areas. So these are the watershed areas around the U.S. And like I said, this is where about 80% of the commercial fisheries depend on these areas for that energy exchange and for that food. Well, here's another map. And this is a map of the U.S. population. And side by side, you can see that, the redder areas are where more people live. And it's definitely ties right into these coastal areas, to these estuaries, in this watershed area. And in fact, about 39% of the U.S. population lives along the coast. I think it's something within 10 miles of the coast. And that's huge. It's, again, it's been that way for a lot of human history. Well, speaking of productivity, you guys have seen this figure before. And this is a global map of productivity. And we already talked about that most of that occurs on the coastline. Well, once again, here's a map of the entire world population. And the same thing, you can see that most of that population is along the coastline. In fact, about 40%, pretty similar to the US, about 40% of the world's population lives along the coast. So the coast is really important. It's a very vulnerable area. There's a lot of things going on here, and we gotta kind of live in harmony. But we're gonna now use this area to talk about some more oceanic processes. And it's a bit of a shorter module. We only have 3 weeks in this one, but we still have a lot of information. So I'm also going to show you that the coastline changes, right? I've already shown you this one figure, right? This U.S. coastline, the light blue surrounded in black, that's our current coastline, right? You can see Florida there. And then if you look at the red line, that was the last ice age, and we already talked about the communities that live further out, like by Block Island, because again, they were following the coastline. They moved themselves out there. And if all the glaciers melt, all the water trapped in ice ends up in the ocean, well, that's that green area, and you can see we lose a lot. So the coastline fluctuates. And you know, the continental margin is going to fluctuate, because we already know that the continental margin is that submerged area of the continent. Well, this is more submerged. So that's the coastline. Now this is something called a eustatic change. So the more water there is in the ocean, we're going to see this around the whole world, right? Every coastline is going to inundate. It's going to move inland a bit. And that's, again, something called a eustatic change. So not just the amount of water, also things like the size of the container of the ocean. And what I mean by that is the actual ocean basin and bottom and crust changes through time. So that container size can actually change, and that's going to affect the coast. Also, things like temperature. So this is where predicting sea level rise again gets more complicated, because as you guys already know, as the temperature of water goes up, density goes down, and it's got to expand, okay? So the volume goes up. So, you know, more water, changes in the container, and changes in the temperature are going to affect things quite a bit. And now the wind's picking up a little bit, and my notes are getting in the way. But we're going to focus more. We'll talk, we've talked a little bit about some of those. We'll talk about some tectonic motion later on. But we're going to focus on what we call local changes. And we've already talked about a couple of these. So wind and currents, right? Wind and currents are definitely going to affect the coastline. The coastline is ever changing. And if any of you have spent much time going to the beach back and forth, you'll actually notice the beaches change pretty rapidly. Pretty much, every year it's a little bit different depending on the currents and the wind. And, the rocky coastlines are going to change too, just maybe not as quickly. But, of course, you already know that this lecture is entitled The Shoreline and Waves. So the other 3 things that we're going to focus on over the next few weeks are waves, storms, and tides, because these have a lot of effect on the coastline. All right, waves are a major effect, and also, again, storms and tides. So with that, I think that's all I wanted to say about the coastline. I'm going to enjoy the rest of the time I have out here on this beautiful day. And once I get around to it, I'll go ahead and meet you guys back inside, and we'll continue our discussion about waves and how they shape the coast. All right, you guys have a beautiful day, and I'll see you in a bit.
Waves, probably one of the most iconic images that people have when you think about the ocean. So we've already said that, humans experience the ocean via the coastline. That is, most humans throughout most of history, this is how we experience it the most. And waves are a big part of that. They stand there, listen to them. They can be soothing or violent or whatever. And they have a big part in shaping that coastline. So I asked you guys at the end of the last module, because this is rather important, what you thought a wave was. So, just to sit back and think about it, you probably experience waves throughout your day-to-day, or at least your week-to-week. But I want to first start by answering that by saying what a wave is not, okay? So I appreciate your responses. Again, all of these things that I'm asking you guys to do, I read every single one of them, and I like that you're thinking about this and getting us moving forward. But what is a wave not? Well, what did we first started this class talking about? We started talking about currents, and we remember that a current is a movement of mass, okay? I'm not going to go back into that, but that was a movement of mass, any kind of current. Well, a wave, again, any kind of wave, is a movement of energy. So there's a little bit of mass back and forth, and I'll show you guys this in a minute, but overall, mass doesn't really move. It's energy that moves. You know, it may use mass, a wave may use mass to move through, but it moves energy. So that important distinction, a current is a movement of mass and a wave is a movement of energy. So before we get into ocean waves, let's just talk about waves in general, sort of like we did currents. And if we look at a wave, any kind of wave, it might look something like this. All right, you guys may have seen this, right? Things move back and forth. And it does appear, again, that this wave is moving in this direction. Well, it is. The wave is moving. But I'll tell you what, focus in on one of those red dots. So each one of those dots, we can think of those as individual particles, all right? So focus in on, let's say, this one right here in the middle, and watch its path. What does it do? Well, it just goes up and down. It doesn't move horizontally. So that's what I mean when I say this is a movement of energy and not of mass, because if each one of these particles is mass, yes, it moves up and down, but it doesn't move along the wave like mass moves along a current, okay? So these nodes, this is called a node, just move in the up and down direction compared to a wave. So again, looking at this wave, we'll just say, if we want to use X and Y axis, that's fine. And a few other terms, just looking at a basic wave we want to talk about, is the first one is the crest. So right there at the top, the crest moves along, and that's the crest of a wave. And then conversely, we have the trough down here in the bottom. So the crest and the trough. The next term is wavelength, and this is going to be a really important one. And the wavelength is the distance either from crest to crest or trough to trough. Should be the same distance. That's your wavelength. That's measured in meters or something smaller, depending on the size of the wave. Another one we want to talk about is the amplitude. Now, amplitude is that distance from the center line of the wave, all right, to either the crest or the trough, all right? That's your amplitude. That's big A. And finally, I already talked about this, the node. A node is just a single particle, molecule, whatever you want to call it, and that moves up and down on this transverse wave. We may talk about other types of waves later on in the semester, but for now, this transverse wave, these are all the parts you need to know. So that is a wave in general. And again, energy transfer along the wave, mass doesn't move that much. So now let's shift to the ocean, because water waves are just one type of wave, okay? And we have some similar things. So you can see here we still have a crest, we still have a trough, we still have a wavelength, okay? We have a distance of direction of travel, and calm sea level is what you can think of, sort of that middle point, that axis, if it were. And one thing a little bit different though, or two things a bit different, is we don't talk about amplitude when we talk about ocean waves. We talk about wave height. And wave height is the distance from trough to crest, so double the amplitude. So make sure you guys get those. If I ask you to label amplitude, label amplitude. If I ask you to label height, it's double that. It's both of those. The other one's really interesting. So when I said that those nodes don't move, well, in the water they move a little bit. And what they do is they travel in a circle. So you can think of each one of those nodes as a water molecule, and what they do is they end up moving in a circle, okay? And I'll show you that a little bit more detail in just a minute. But I want to point out a few things with this that's already on here. So a couple terms we're going to need, and yes, there's going to be some math involved. The first one is frequency, wave frequency. Now, this definition here says the number of waves, crests that pass each second. Sure. Well, frequency is just the number of anything per time. So you could be standing on the highway and it's the number of cars that pass you in an hour. It could be in the grocery store and it's the number of boxes of, Cheez-Its that get thrown at you. I don't know why that would happen, but that's all I could think of right now. So anyhow, put into an equation term, F, that squiggly f is equal to the number of something per time. And in our case, we are going to use seconds. And if seconds is on the bottom, our units are 1/2, which is called a hertz, H-E-R-T-Z, or Hz. So those are your units. So make sure that when you do these problems, right, if you have frequency, you set up your equation, you say that's 1/2, and then you use hertz, just like we've been doing all along. The next one is the period. This one's fairly simple. It's just the inverse of frequency. So the time required for a wave crest to go from A to B. Well, what you'll notice is A to B is just crest to crest. So the time for one wave to go is just period T, big T, is equal to 1 over the frequency. That's all it means. And that's just in seconds. So the period is however many seconds it takes for a wave to go its own wavelength. That's the period. So those two equations. So the next thing, I'm going to come back to this node traveling in a circle. And if you look at the waves, broadly, it's going to look something like this. All right. So what we're going to say is each one of these yellow dots, again, there's a lot more than this, but we'll look at those as individual water molecules. And up here at the surface, where you can really see that wave traveling, you'll notice these little molecules move in a circle, all right, as the wave moves. And you guys can pause this and look at it and see how this works, but that gives you a wave. But what you'll also notice is that as you travel down in the water, the circles get smaller and smaller. So they still travel the same point. So even way down here, when the water molecule's on the bottom of the circle, it's on the bottom of the circle here, and so on and so forth. But those circles get smaller. In fact, this is a really important distinction, is below this level, you pretty much don't have any wave motion. So all that energy is contained up high. So below here, that's it, no more wave. The wave is totally contained in this upper part. And there's a specific relationship for that. So this depth is a depth of the wavelength divided by 2. So half of that wavelength. So you guys can see here, if I measure out one wavelength, I cut it in half, and I stick it down in the water, it reaches right about here. So that's an important distinction, that wave motion is negligible, deeper than half of the wavelength. Okay, that's enough of that. Well, the next thing we want to talk about, now that we kind of see the structure of a wave, is how we get here. Well, we know if you go out in a storm and stand by the shore, you're going to have some massive waves, but they don't start out that way, all right? And I don't want to use the term just like currents, but the driving force for these waves is wind, like surface currents, the driving force. But again, it's now transferring that wind energy to the water, and the water's carrying the energy forward, not necessarily the mass. But it doesn't just start that way, right? A storm doesn't start and all of a sudden, the sea's enormous and then it dies, right? There's a progression. And so that's the thing we're going to talk about next. We're going to go through and see how these waves actually develop. So the first thing to note is they start out, a wind starts to blow and you get something called a capillary wave. And you guys may know these as ripples on the water. So you've seen something like this, just as that wind starts to blow, we get these little ripples. And they're very specific, and they're called capillary waves for a reason. You'll notice here, we've defined them as 1.73 centimeters. So anything less than that 1.3 centimeters is a capillary wave. So this brings me to why it's so specific. We want to talk about something called a disturbing force and a restoring force. So a wave has a disturbing force, and that is the thing that makes it start to move. So we just said, in this case, wind. Wind starts to blow, it disturbs the water, and the water starts to make these capillary waves. And oh, by the way, all the waves that we're talking about, at least for now. Well, we have something else called a restoring force, and that's what makes it stop. So when the storm goes away, the waves are still pretty big, right? Just because the wind goes away doesn't mean that the waves stop. They still contain all that energy. So something has to slow them down. And in the case of capillary waves, they're named that way because of their restoring force, all right? This 1.3 centimeters has to do with something we talked about earlier, and it has to do with those hydrogen bonds in water molecules, all right? You end up with that cohesion. Those molecules stick together. Well, that's called capillary action. So as those molecules are moving around, there's a tendency for them to want to stick together. And that force is going to slow down the wave action. And it just so happens that once you surpass 1.73 centimeters, that is overridden. That capillary action is not strong enough to slow these waves down, all right? So that brings us into our next progression. So the wind keeps blowing. We end up in our next zone, something called gravity waves. And again, like I said, these are named after their restoring force. So for a gravity wave, we still have the same disturbing force. It's just still the wind. But because they've gotten too big, they've gone past that 1.73 centimeter wavelength, we now have to have something else, and it's just gravity. Remember, gravity pulls everything with mass down to Earth. So over time, that force pulling down towards Earth will smooth everything out. But to get there, for this wind to happen, we have to get to this point. We have to get to these gravity waves. We have to get to these, what I'll call a fully developed sea, all right? And that takes three important things. The first thing is wind strength, right? How powerful is that wind? That should be pretty obvious, right? A less powerful wind isn't going to generate waves as big as a more powerful wind. But we already said that that's not enough, right? The storm doesn't just happen and all of a sudden massive waves. We need something else. So the second thing is something called wind duration, basically just time. How long is that wind blowing for in a certain direction? If a big gust just comes by, not much is going to happen. You might get some ripples of capillary waves. So strong wind over time. The third one is something called fetch. Now fetch is the uninterrupted distance that this wind blows. Give you an example of that. If you look at, let's say, Greenwich Bay, right? It's a small enclosed area. It's not very big. And what that means is no matter how powerful a wind is, if it blows for a really long time, the waves will never get that high because it wasn't blowing for long enough distance, okay? We need distance. We need a long distance surface area for the wind to transfer more and more energy to the ocean. So blowing all the way across the Atlantic or the Pacific will give you much bigger waves than in a bay. So for a fully developed sea, we need wind strength, wind duration, and fetch. So a strong wind blowing for a long period of time over a long distance. That's your fully developed sea. So that's where we are in gravity waves. And as you guys know from standing on shore or just watching out in the water, what's the next thing that happens? Well, waves don't get incredibly big, right? They don't just keep getting bigger and bigger and bigger. They have to stop at some point. And we can see this, we can see white caps forming out on the bay. Like they get to a certain point and they basically topple over. And that's where we have this next relationship, all right? This wave height and we have a wavelength, all right? That's what happens next. And critically, this critical steepness, this h over L, so wave height over wavelength, is 1/7. Once it gets bigger than 1/7, a wave can't sustain itself anymore, and it's going to topple over. So that's what we mean by that. No, I don't mean waves that come up on shore and crash. That's a different thing, but which I'll talk about in a minute. This is just out in open water. Now you might be saying to yourself, well, that doesn't seem like that much, right? I know I've seen waves. I mean, you look in movies and you see these ships and these waves, these enormous waves out at sea, taking them over. Well, you're right. That brings us to our next little bit here is waves interacting. Okay, so one wave left alone on its own will never get bigger than this. However, something else that we have is something called interference, all right? These waves actually act together to interfere with each other. So let's pretend we have two waves. Right? We'll go back to our simple wave diagram. We have wave X and wave Y, all right? Stacked on top of each other, and we're going to add them together, all right? These are interacting, these are interference. Well, what you'll notice here is for every crest and every trough, they line up. They're perfectly in line with each other. These are the same waves right on top of each other, and they line up. Well, in this case, we get something called constructive interference. So if we add them together, the resultant wave Z looks exactly the same, it's just double the size. So double the wave height. So what we've done is we've taken wave X and Y, right? These are two fully developed waves that if they got any bigger, they would crash over on each other. And we've added them together. And we actually get a bigger wave. In fact, you can get something so big, this is something called a rogue wave. I mean, you maybe seen these in movies and stuff. They're just beyond what is theoretically possible. And again, this is called constructive interference. Well, we can do sort of the opposite of that. So if we take our wave x, we'll keep that one the same, and we make wave y just offset, so a half a wavelength different to where the trough of wave x lines up with the crest of wave y. And what you end up with, if you add those together, is nothing, is flat. They actually cancel each other out. In fact, this is similar to the way noise-canceling headphones work. It actually feeds you a frequency to counteract the background noise. And to your ear, everything's canceled out and you can't hear it. And this is called destructive interference. So a combination of constructive and destructive interference will give you something that looks like this. So you'll notice at the top, we can call that wave x again if we want. And then the wave below it is moving. It's constantly moving in this direction. And you'll see the resultant wave, depending on where that wave is either double the size or flat, and it moves back and forth. And again, in the ocean, this gets a lot more complicated than this, right? Waves come from all different directions, they collide, all that stuff. But the important part is here you get this constructive and destructive interference. And you can get something kind of cool. If you've ever seen a wave table, it looks a little bit like this. We have a source of a wave, or in this case, I guess, two sources. And what you'll end up with is these lines here, the darker, you call the white ones crest and the dark trough. And then you'll see kind of in between them, it's just flat. There's nothing there. So again, constructive and destructive interference. The next thing I want to talk about are some broad categories of waves because it affects how they behave. So if you guys remember, we already saw this figure showing you the circles of these nodes traveling, and I said that this means that below this level, right, below that line of no movement, that was about half the wavelength deep. So if the water depth is deeper than that, it's something called a deep water wave, right? This is a wave traveling in water deeper than half the wavelength. What that means is if it's shallower than that, we'll get to our shallow water wave, but importantly, this doesn't necessarily mean deep water. So I'm going to talk about a deep water wave and a shallow water wave. It has more to do with the relationship of wavelength to depth, okay? So deep water wave, the water depth is greater than half the wavelength. Well, speed has something to do here. So this wave is going to behave in such a way that the speed of the wave, right, the velocity, is equal to its wavelength times its frequency. It looks just like this, all right? So if I were to ask you to calculate the speed of a wave and I gave you some parameters, this is what you're going to do. And notice that these units line up, right? Meters would be the unit for wavelength, and per second is frequency. Meters per second gives you velocity, gives you speed. Okay, so this is a deep water wave. Well, a shallow water wave is a little bit different. And remember, a shallow water wave now is a wave traveling in water that's much shallower than half its wavelength. There are some numbers thrown out there, I think less than 20 times that, but let's just stick with this equation here. Water depth is much, much less than half the wavelength. That's all. And velocity behaves a little bit differently too, all right? So instead of just being the wavelength times the frequency, it's now the square root of gravity times the depth, all right? So we've gone from frequency and wavelength affecting the speed to just water depth. And I'll show you why that is here in a second. So if I take this figure, and this is showing you a progression of a wave. So you can see here, this is where it is a deep water wave because depth is greater than half the wavelength. And then it becomes a shallow water wave because all of a sudden it starts to feel the bottom. And a few things happen when it starts to feel the bottom. Number one, you can sort of see here in these circles, they don't stay circles. They start to turn elliptical. So those nodes turn elliptical, okay? And again, then you have this speed change, all right? So all that velocity, all that energy starts to squish these waves together and they get taller. And again, yes, then they crash on the shore. But this is that progression. This is how we go from deep to a shallow water wave. And again, this is different than that relationship of 1/7. That's for breaking out in open ocean. This is specifically because we meet the bottom and the waves have nowhere to go but up and over, all right? So deep water wave, wave traveling in water depth deeper than half its wavelength. Shallow water, less than half its wavelength. And you need to remember these equations if I ask you what these differences are and to explain this progression. All right, so what else? So that's That's waves, right? This is one of the main things that affect our coastline. And next we're going to move into storms. Well, something I want you guys to think about before I give you that lecture, before I give you that information, is we already know, okay, storms are powerful winds. And we talked earlier about wind movement around the planet. We already know that winds move from high pressure to low pressure. We know how all this works. But something else. So I did use the atmosphere when I talked about the hydrostatic pressure equation, but it's not that simple. All right, so if you just take the hydrostatic pressure equation, this works really well in the ocean because gravity doesn't change and density doesn't change that much. All right, so everything's dependent on that water depth. Well, in the atmosphere, density is not constant. The air at the surface of the planet is much more dense than the air as you move upward into the atmosphere. So what I want you guys to do is I want you to think about this. If you can't use the hydrostatic pressure equation, at least directly, to measure the pressure in the atmosphere, how would you do it? What would you do? What maybe trickery or mechanism would you use to be able to measure the pressure at one location? Because this is exactly what weathermen are going to do when they predict where storms are going to move. They have to get that atmospheric pressure. So how would you do it? So think about that, answer that question, and again, look ahead towards the next homework assignment. Come to me with questions if you have them, and I'll see you next time to talk about storms and hopefully answer that question for you.